Here's the halfway point for the SAR ADC, to which I will demonstrate the sample and hold IC and how an op-amp is used to compare its output to that of an R2R ladder digital to analog converter. Throughout the video, a DMM will be used to demonstrate voltages. For example, let's say the input voltage is 1.58 volts. First, I'll adjust the trim pot to do so. When I press this button, it will trigger the IC, causing its output to hold the trim pot at that output. So first, I'll measure the voltage with the DMM at the output, and right now it's at 1.13 volts, which is just from the previous input before I recorded this video. And as soon as I press this button, you'll see the output goes to exactly 1.58 volts. And when I let go, this capacitor will slowly discharge, decreasing the voltage over time. As you can see, when I change this potentiometer, nothing will happen to the output of the sample and hold IC because I'm not pressing the button. Next, the R2R ladder is used to create an analog signal as close as possible to the desired sample voltage. It does this by using successive approximations. So quickly, I'm just going to move the DMM to measure the output of the DAC. And though I'm going to do successive approximation manually right now, the final circuit does it by itself. And it begins at the MSB, which is the leftmost switch, which holds 1/2 of the reference voltage. Since the reference voltage is 5 volts, the output when the MSB is on will be 2.5 volts. And as you can see when I turn on the MSB, approximately 2.5 volts show in the DMM. So right now when I put on 2.5 volts, you can see that the comparator output goes low, because it means that the ladder output is greater than the sample and hold output. And if we didn't know that the original voltage was 1.58 volts, we now know that the original voltage is less than 2.5 volts because the comparator output is low. We will then move on to the second most significant bit at 1.25 volts. And as you can see, the comparator goes high because 1.58 volts is greater than approximately 1.25. And as I continue this process, the DAC output gets closer and closer to the original sample voltage. So our final DAC output is 1.58 volts, which is very close to the original 1.575 analog input. The circuit begins with the R2R ladder. The R2R ladder works by taking a reference voltage and some number of switches. From right to left goes MSB to LSB, where the rightmost switch supplies half of the reference voltage, 2.5 volts, and the LSB, for 8 switches, provides 1/256 of the reference voltage, or 1/2 to the power 8 of the reference voltage. And in Fallstad, it provides 29 millivolts, but in theory, it should be around 19. The next thing I'm going to talk about is the plus and minus 9 volt power supply that is used for the sample and hold IC. In order for a comparator to work, it needs the input voltages to be within the rails of its positive and negative inputs. To my understanding, since we are dealing with 5 and 0 volt inputs, an AC waveform centered at these points will get cut off, as its waveform fluctuates beyond the cap. Here's a Fallstad simulation of an AC waveform at 0 volts. When the op-amp is set from 5 to 0 volts, the output fluctuates as it cannot pick up voltage less than 0. But when the low rail is set to negative 5 volts, the op-amp can pick up the entire signal. In this project, 2 9 volt power supplies are used, where the positive of one side is connected to the negative of the other. To then get a 5 volt power supply for all other components, an LM7805 voltage regulator is used.